Imagine you throw a ball. Does it take just one path? Or does it take millions of paths simultaneously, even going around the moon and back? Sounds crazy, right? But in the 1940s, a young physicist asked a question that completely revolutionized quantum physics. His name was Richard Feynman. And in this video, we're going to understand how this question solved one of the deepest mysteries of reality itself. It's the 1940s, an MIT classroom. A professor is explaining the double-slit experiment. Electrons are being fired one at a time toward two slits. Since we can't say for certain which slit the electron went through, quantum mechanics tells us it goes through both slits simultaneously. The professor is beautifully drawing the interference pattern on the blackboard, showing how two waves add up to calculate probability. Right then, a hand shoots up from the back row. "Sir, what if there are 3 slits?" The professor, slightly annoyed, replies, "Then you add the wave amplitudes from all 3 slits. Simple." "What about 4? 5? The professor, now clearly losing patience, says, "Look, the whole class understands. You add the amplitudes from all slits. 6, 7, however many." But the student doesn't stop. "Then, sir, what if there are infinite slits, meaning the entire screen disappears, and then another screen with infinite slits, then another? The entire classroom goes silent, because this question means even when we're not doing a double-slit experiment, when a photon or electron is just traveling through empty space, it's exploring all possible paths simultaneously. This story might be made up, but the logic came from Richard Feynman. And from this one question was born a completely new approach to quantum mechanics, the path integral formulation. But where did this idea come from? To understand that, we need to go back further, to 1900, to Max Planck. The 1890s. Electric lighting was just arriving in Germany. The era of gas lights was ending. The German government wanted to replace all streetlights with electric bulbs, but the problem was, how do you extract the maximum visible light from a hot filament? A German research institute called PTR started working on this. They discovered that when any object heats up, it emits light. At low temperatures, each material gives off different colored light, but above 500 degrees Celsius, all materials start emitting the same kind of light. The hotter it gets, the more energy, and the peak wavelength shifts toward shorter wavelengths. But why? What's the theoretical explanation? They imagined the simplest possible object, one that would absorb all light and perfectly emit radiation based on its temperature. They called it a blackbody. They designed a metal cube with a small hole. This hole is a perfect blackbody. Any light entering it bounces around and gets absorbed. Theorists said the electrons in the cube's walls would vibrate, creating electromagnetic waves. These waves would bounce off the walls. When two waves of the same frequency, one going right, one going left, interfere, they create standing waves. These standing waves are what survive, and the shorter the wavelength, the more standing wave modes can fit. In 3 dimensions, the number of modes is roughly proportional to the cube of frequency. This led to the Rayleigh-Jeans law. At long wavelengths, it matched experimental data perfectly, but at short wavelengths, the theory predicted infinite energy would be emitted. This became known as the ultraviolet catastrophe. Max Planck almost didn't become a physicist. At age 16, he asked his professor about a career in physics. The professor told him, "Find another field. Physics is essentially complete, just a few tiny problems left to clean up." But Planck didn't listen. By 1897, he was a professor himself. And for the next 3 years, he desperately tried to find a theoretical explanation for blackbody radiation. He later wrote, "I was ready to sacrifice every one of my previous convictions about physical laws." Then, in what he called an act of desperation, he tried something no one had thought of. According to classical physics, the energy of an electromagnetic wave depends only on its amplitude. It could take any arbitrary value. But Planck tried restricting energy. It could only come in multiples of a smallest amount, a quantum. And he made the energy of one quantum directly proportional to its frequency. E equals hf, where h is just a constant. Think about what this does. At a given temperature, the atoms inside the cavity have a range of energies. Some have a little, a few have a lot, most are somewhere in between. For long wavelength, low-frequency radiation, the energy hf of one quantum is small, so all atoms have enough energy to emit this wavelength. But at shorter wavelengths, higher frequencies, the energy of one quantum increases. Now not all atoms have enough energy to emit that wavelength. This is why experiment diverges from classical prediction. The spectrum peaks and then starts falling, because fewer and fewer atoms have enough energy to emit one quantum of that radiation. And there comes a point when no atoms have enough energy, so the spectrum must drop to zero. The ultraviolet catastrophe is solved. Planck tuned the parameter h to perfectly match experiment, but he was troubled by his own formula because to him it was just a mathematical trick. He had no clue why it worked. He wrote, "A theoretical interpretation had to be found at any cost, no matter how high." After weeks of intense work, he had a realization. Planck's constant h has the units of action. Remember, in a previous concept, Maupertuis proposed that everything in nature follows the path that minimizes action. Action equals mass times velocity times distance. Planck proposed h is a quantum of action. Anytime any change happens in nature, it would be some whole multiple of this quantum of action. At first, the quantum of action got little attention until a 26-year-old patent clerk came on the scene.
In 1905, Albert Einstein claimed that Planck's theory wasn't just a mathematical trick. Light actually comes in discrete packets, or photons, each with energy hf. Einstein used this insight to explain the photoelectric effect, how light can eject electrons from metal, but only when the frequency is high enough. If the frequency is too low, no electrons will be emitted regardless of intensity. Because each photon is a separate packet, ejecting one electron requires a specific minimum energy. Low frequency means low hf, so one photon doesn't have enough energy. The idea of quantization spread. 11 years later, in 1913, Niels Bohr was wondering, why is an atom stable? A positive nucleus in the center with negative electrons whizzing around it. Classical physics says these electrons should spiral into the nucleus, radiating energy as they go. But that doesn't happen. Why? Bohr came up with a crazy idea. Angular momentum is quantized. Angular momentum equals mass times velocity times radius equals mvr. This also has the same units as action. Bohr said mvr equals n times h bar, where h bar is h divided by 2 pi and n equals 1, 2, 3. Why? No good reason. Completely ad hoc. But it worked. It gave the correct energy levels of the hydrogen atom. When an electron jumps from a higher orbit to a lower one, the energy difference is given off as a photon of a particular color of light, exactly reproducing the hydrogen spectrum. But why is angular momentum quantized? Nobody knew. 11 years later, in 1924, Louis de Broglie had an incredible insight for his PhD thesis. If light can be both wave and particle, then maybe matter particles can also be waves. He proposed everything has a wavelength. Lambda equals h divided by p equals h divided by mv, where p is momentum. Now think, if an electron is a wave, then to stay bound to a nucleus in an atom, it must exist as a standing wave. This requires that a whole number of wavelengths fit around the circumference of the orbit. 2 pi r equals n times lambda. Substituting de Broglie's expression, 2 pi r equals n times h over mv. Rearranging, mvr equals n times h over 2 pi equals n h bar. That's it. Bohr's quantization condition. But now we know why. Because electrons are waves, and to be bound in atoms, they must exist as standing waves for constructive interference. That's pretty good. You can get a PhD out of that. But this has a deep implication. If electrons, photons, everything is a wave, then they no longer have a single path through space. They must explore all possible paths. I've thought about and taught the double slit experiment hundreds of times without fully realizing this implication. In the double slit, we say, since we can't say for certain which slit the particle went through, quantum mechanics tells us it goes through both slits simultaneously. To get the probability of finding a particle somewhere on the screen, amplitude of wave going through the first slit plus amplitude of wave going through the second slit, add and square. This is the interference pattern. Now Feynman's question. What if there are 3 slits, 4, 5? Same. Add amplitudes from all slits. What if there are infinite slits?
Then there's no screen, just empty space. And then more infinite slit screens. More. This means even when we're not doing a double slit experiment, when a photon or electron is traveling through empty space, it's exploring all possible paths. Feynman said, anytime any particle, photon, or even macroscopic object goes from point A to point B, it has some chance to take any path, even paths faster than light, paths going backward in time, paths going around the moon and back. However crazy the path might be, and we need to include all these paths in our calculation, each path weighted the same. Sounds insane? Then the question is, why don't we see all those crazy paths? The answer lies in how we add up the amplitudes. To understand simply, imagine 3 paths. For each path, we'll start a stopwatch. As the particle wave follows that path, the stopwatch hand spins very fast. When it reaches the endpoint, we stop. We'll get 3 arrows for 3 paths. We'll take their vector sum, then square. That's the probability. If the arrows point in random directions, the vector sum will be small, meaning low probability. But if all 3 arrows point roughly in the same direction, then the vector sum is large. High probability. The larger the resulting arrow, the higher the probability of that event happening. Now the big question. What is the stopwatch actually measuring? Not actually time. It's measuring something called phase. Just like in the double slit experiment, when a wave takes a different path from point 1 to 2, it arrives there with a different phase. This phase determines the amplitude of the wave at that point. Mathematically, amplitude equals e to the I phi, where phi is the phase. As the particle wave follows a path, its phase increases, winding the vector around. So how much does the phase change for each path? Imagine we split the path into many tiny sections, each one so small it's effectively straight. In each small section, the particle goes a distance delta x, takes time delta t, and velocity v equals delta x over delta t. In this small section, phase change delta phi is proportional to something. Feynman showed delta phi is proportional to kinetic energy minus potential energy times delta t. Or delta phi is proportional to Ke minus Pe times delta t. For the entire path, phi equals 1 over h bar times the integral of Ke minus Pe dt. Wait, does this integral look familiar? The integral of Ke minus Pe dt, this is action. Hamilton showed that action is the integral of kinetic minus potential energy. So phi equals s over h bar, where s is action. Phase is action divided by Planck's constant. Everything is coming together. Now the real magic. Imagine you throw a ball. We said the ball is exploring all possible paths, but we only see the ball taking one path, a parabolic path. Why? The reason is hidden in phase cancellation. For a macroscopic object, the action s is a very large number, and h bar is very small. H bar is approximately 10 to the minus 34 joule seconds. So phi equals s over h bar will be a huge number, meaning the stopwatch hand is spinning crazily fast. Now imagine 2 paths slightly different from the classical path. First path's action equals s plus delta s. Second path's action equals s minus delta s. Their phases will be first s plus delta s over h bar, second s minus delta s over h bar. Since h bar is so small, no matter how small delta s is, the phase difference is huge, meaning the two arrows will point in nearly opposite directions. They cancel out. All the crazy paths cancel each other out, but there's one path that survives. Which path? The path where action is minimum or extremum. Paths near this path have nearly equal action, so their phases are also nearly equal, so they constructively interfere. This is the classical path, the principle of least action. Maupertuis, Lagrange, and Hamilton, everyone said action is metamized, but Feynman showed actually all paths are being explored. Only the paths near the action extremum survive. Now take an electron. For an electron, the action s is much smaller, so small that it's close to h bar. Then phi equals s over h bar is no longer huge. The stopwatch hand isn't spinning that fast, so many different paths can have phases close to each other. They all constructively interfere. That's why for quantum particles, many paths are equally important. That's why we see interference patterns in the double slit. What about light? For photons, energy E equals hf. For visible light, this is small. So photons also explore many paths. But when light intensity is high, meaning millions of photons together, averaging gives the classical path. Remember the beach example? Which path to take to save your friend? Light takes the least time path, Fermat's principle. But actually, light is exploring all paths. Only paths near the least time path add constructively. This is nature's greatest illusion. Richard Feynman developed this entire framework in the 1940s. He showed that any quantum mechanics problem can be solved this way. Add up the amplitudes of all possible paths. Mathematically, amplitude from A to B equals the sum over all paths of e to the is over h bar. This is called the path integral formulation. This is the third major formulation of quantum mechanics: Heisenberg's matrix mechanics, Schrödinger's wave mechanics, and Feynman's path integral. All three are equivalent, same physics, different language. But Feynman's method gives an incredible intuition, the connection between quantum and classical mechanics. This method isn't just for particles. Feynman applied it to quantum electrodynamics, or QED. QED is the quantum theory of electrons and photons, the most successful theory in physics, matching experiment to 12 decimal places. Feynman diagrams, which are now the language of particle physics, came from this path integral approach. Each diagram represents a possible path. Add up all diagrams to get total probability. What does this theory tell us about reality? 1. No determinism. Particles don't take a definite path. They take all paths. We can only talk about probability. 2. Locality is questionable. A particle can go around the moon to get from point A to B, though the probability is extremely low. 3. The nature of time. Some paths go backward in time. Feynman explained antimatter as particles going backward. 4. The centrality of action. Action, which started as a vague concept, became the heart of quantum mechanics. Richard Feynman, 1918 to 1988, wasn't just a great physicist, he was an extraordinary teacher. His famous quote, "If you can't explain it simply, you don't understand it well enough." He could explain complex ideas simply, played bongo drums, made jokes, but never lost depth. In 1965, he received the Nobel Prize for QED. But his greatest contribution was teaching us to see quantum mechanics with new eyes. We started with a simple question. When I throw a ball, does it take just one path? Now we know, no. The ball, the photon, the electron, everything is simultaneously exploring all possible paths, going around the moon, faster than light, backward in time, all paths. But most paths cancel each other out. Only paths with nearly equal action add constructively. For macroscopic objects, only the action-minimizing path survives. For quantum particles, many paths survive. This is the bridge between quantum and classical. And at the center of it all is action, that mysterious quantity Planck discovered in an act of desperation. And Feynman showed this action is the key to phase, which determines which paths actually happen. Next time you throw a ball or turn on a light, remember, what you see, that single definite path, is actually the sum of countless possibilities. Nature is testing every possibility. The quantum wave is spreading through thousands of paths, but when all the path amplitudes add up, magically a coherent picture emerges. This is reality. And Richard Feynman, a curious student who wasn't afraid to ask crazy questions in class, taught us to see this deep truth. In his own words, nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. The quantum world is strange, but it's our world. And in this world, everything is connected to everything else through all possible paths.